cosm. Whoosh.
The universe is big. Andromeda is far away, but we can still reach it with our minds, with our telescopes, with our theories and equations. We can still understand it, still learn from it, still be awed by it. And that's enough. That's more than enough. That's everything. There's another dimension to Andromeda that deserves attention. The galaxy is moving through space, and that motion tells us something profound about the universe's structure. Andromeda isn't just approaching the Milky Way. It's part of a larger flow of galaxies, all moving together through space, pulled by massive concentrations of matter we can barely detect. The local group, our cosmic neighborhood, is falling toward the Virgo cluster at about 400 kilometers per second. But even the Virgo cluster is moving, falling toward something larger. We call it the Great Attractor, though that name is somewhat misleading. It's not a single object, but a region of space where mass is concentrated, creating a gravitational well that pulls everything nearby. Beyond the Great Attractor lies an even larger structure, the Shapley supercluster, containing thousands of galaxies, exerting its own gravitational influence across hundreds of millions of light-years. These motions reveal the universe's large-scale structure. Galaxies aren't distributed randomly. They're organized into a hierarchy, from pairs to groups to clusters to superclusters, all connected by the cosmic web. And this structure arose from quantum fluctuations in the early universe, tiny variations in density that got amplified by gravity over billions of years. The pattern we see today, the distribution of galaxies, the voids and filaments, all of it traces back to those primordial fluctuations, to quantum uncertainty in the first fraction of a second after the Big Bang. Think about that chain of causation. Quantum fluctuations, impossibly small variations in energy density, occurring in the first 10 to 43 seconds of the universe's existence, led to the formation of galaxies billions of years later. Led to stars, planets, life, consciousness. Led to you sitting here, reading these words, contemplating the cosmos. The universe is connected across time and scale in ways that are almost incomprehensible. Everything is linked to everything else all the way back to the beginning. Andromeda is part of that story. Its position in space, its motion, its structure, all of it is determined by initial conditions set in the first moments after the Big Bang. The galaxy couldn't be anywhere else, couldn't be moving in any other direction. Its fate was written in the quantum foam of the early universe, encoded in fluctuations that occurred before atoms existed, before matter as we know it existed. Determinism on a cosmic scale. But there's also randomness, chaos, unpredictability. The exact details of Andromeda's structure, the number and distribution of stars, the patterns of spiral arms, these weren't predetermined. They emerged through processes that involve chance as much as necessity. Star formation is chaotic. Turbulence in gas clouds creates unpredictable patterns. Supernovae explode at random times and places, scattering material in unpredictable ways. The universe operates at the intersection of order and chaos, determinism and randomness, law and chance. This interplay creates complexity. Simple laws like gravity and thermodynamics, operating over long timescales, generate intricate structures. Galaxies with spiral arms, star clusters, planetary systems, and on at least one planet, life. Simple chemistry following basic rules led to self-replicating molecules, which led to cells, organisms, ecosystems, intelligence. Complexity emerging from simplicity, order arising from chaos. It's one of the deepest mysteries in science, and we're only beginning to understand it. Andromeda represents one outcome of this process, a galaxy that formed, evolved, grew through mergers, settled into a stable spiral structure. It's one of countless galaxies, each with its own history, its own unique configuration. No two galaxies are exactly alike. Each is a singular creation, a unique arrangement of matter shaped by billions of years of cosmic evolution. Let's consider what happens on shorter timescales in Andromeda. Right now, at this very moment, stars are being born. Gas clouds are collapsing under their own gravity, fragmenting into clumps, heating up as they compress. When the temperature at the center reaches 10 million degrees, hydrogen fusion ignites. A star is born. This is happening thousands of times per year in Andromeda. Thousands of new stars, each one a fusion reactor, each one capable of shining for millions or billions of years. And stars are dying. Massive stars are going supernova, exploding with the force of a billion suns, briefly outshining the entire galaxy. White dwarfs are slowly cooling, fading into darkness. Neutron stars are spinning, beaming radiation into space. Black holes are accreting matter, emitting X-rays as material spirals into the event horizon. The galaxy is alive with activity, constantly changing, never static. On planets orbiting some of those stars, weather patterns are shifting. Storms are brewing. Volcanoes might be erupting. Earthquakes might be shaking continents. And maybe, just maybe, organisms are living, reproducing, evolving. Maybe somewhere in Andromeda, at this exact moment, a creature is looking up at its sky, seeing the Milky Way, wondering if anyone is out there. Maybe they're pointing telescopes at us, trying to detect signs of intelligence, searching for a signal that never comes. Or maybe not. Maybe we're alone. Maybe in all of Andromeda's trillion stars, in all its billions of planets, life never emerged. Maybe Earth is unique, the only place in two galaxies where chemistry became biology. We don't know. We can't know, not yet. But the question haunts us, drives our curiosity, fuels our exploration. The search for life, for intelligence, for other minds in the universe is one of the most profound scientific endeavors we've undertaken. It's not just about finding aliens. It's about understanding our own existence, our own uniqueness or lack thereof. Are we common or rare? Product of inevitable processes or incredible luck? The answer would change how we see ourselves, how we value our existence, how we think about our future. If life is common, then the universe is teeming with it. Every suitable planet hosts organisms. Evolution is universal. Intelligence emerges naturally given enough time. And we're just one instance among countless billions. That would be humbling, but also comforting. We wouldn't be alone. Somewhere out there, others are looking up, asking the same questions we're asking. But if life is rare, if Earth is a cosmic fluke, then we're desperately alone. The only consciousness in a vast, empty universe. The only place where matter has organized itself into thinking, feeling beings. That would be terrifying, but also empowering. It would mean we're precious, irreplaceable, the only witnesses to the universe's majesty. Our survival would matter not just for us, but for the cosmos itself. We don't know which scenario is true. Andromeda might be full of life or utterly barren. We're searching, listening, analyzing, but so far, silence. The cosmic silence is deafening, and its meaning remains unclear. Let's shift perspective again. Imagine you're an astronomer on a planet in Andromeda, observing the Milky Way. What would you see? A spiral galaxy similar to your own, containing hundreds of billions of stars. You'd measure its distance, about 2.5 million light-years. You'd note its structure, its spiral arms, its central bulge. You'd observe that it's approaching, that in billions of years, the galaxies will merge. You might wonder if life exists there, if anyone is looking back at you. And you'd be right. We are looking back, but you'd never know it. Our signals, our radio and television broadcasts haven't reached you yet. They're still spreading outward at the speed of light, and they won't arrive for another 2.5 million years. By the time they do, your civilization might be gone, extinct, evolved into something unrecognizable, or transcended into a form we can't imagine. The signal would arrive, be detected by whoever or whatever is there, and they'd realize they were receiving a message from the past, from a civilization that existed millions of years ago. This is the fundamental challenge of interstellar and intergalactic communication. Time delays make real-time conversation impossible. By the time you receive a message and send a reply, the sender might be gone. It's like trying to have a conversation with someone who lived in a different geological epoch. You can leave messages for each other, but you can never actually talk. Some scientists have proposed solutions. Maybe we could encode our consciousness digitally, create virtual representatives that could wait patiently for replies. Maybe we could develop some form of faster-than-light communication, though physics suggests this is impossible. Maybe we'll just have to accept the limitations, conduct conversations that span millions of years, each message a time capsule sent to an unknown future. Or maybe communication isn't the point. Maybe the point is just to know we're not alone. Even if we can never meet, even if we can never talk, just knowing that other minds exist out there, asking the same questions, feeling the same wonder, that might be enough. The photographs taken by Hubble of Andromeda contain over 100 million stars. Each pixel in those images represents multiple stars, each with its own story. Some are young, just beginning their lives. Others are old, nearing the end. Some are in binary systems, locked in gravitational dances with companions. Others are solitary, wandering alone through space. Each one is a world unto itself, a fusion reactor converting mass into energy, shining for millions or billions of years before dying. And around some of those stars, planets orbit. Rocky worlds, gas giants, ice planets, maybe even ocean worlds covered entirely in water. Some are scorched deserts, tidally locked to their stars. Others are frozen wastelands, far from any source of warmth. A few might be just right, temperate and stable, with liquid water and atmospheres. Those are the ones that interest us most, because those are where life could exist. Detecting planets in Andromeda is currently impossible. They're too far away, too small, too dim. Even in the Milky Way, we can only detect planets around relatively nearby stars, within a few thousand light years. Andromeda is 1,000,000 times farther. We'd need telescopes far more powerful than anything we currently have. But maybe someday, technology advances exponentially. What's impossible today might be routine tomorrow. Future telescopes might be able to detect the light from planets in Andromeda, analyze their atmospheres, look for biosignatures like oxygen or methane in combinations that suggest biological activity. We could study alien worlds without ever visiting them, characterize their climates, their compositions, their potential for life. It would be remote sensing on a cosmic scale, astrobiology from millions of light years away. But even if we detect biosignatures, we wouldn't know for sure. Abiotic processes can produce similar signals. We'd need more data, more observations, better models. The first detection of life beyond Earth, if it comes from spectroscopy of distant planets, will be tentative, uncertain, hotly debated. It will take time to confirm, to build consensus, to be sure. Science is careful, methodical, skeptical. We don't jump to conclusions. We gather evidence, test hypotheses, consider alternatives. That's the process, and it's slow, but it's reliable. Consider the energy budget of Andromeda. The galaxy emits light across the electromagnetic spectrum, from low-energy radio waves to high-energy gamma rays. Most of the emission is in visible and infrared wavelengths, produced by stars. But there's also radio emission from gas clouds and supernova remnants, X-ray emission from accreting black holes and neutron stars, ultraviolet emission from young, hot stars. All of this represents energy being radiated into space. Energy originally produced by nuclear fusion in stellar cores or by gravitational infall onto compact objects. The total luminosity of Andromeda is about 25 billion times the luminosity of the Sun. That's an enormous amount of energy, equivalent to converting millions of tons of matter into pure energy every second. And it's been doing this for billions of years, steadily converting mass into radiation, gradually dimming as fuel supplies run low and stars die off. Where does that energy go? Most of it just disperses into space, absorbed by dust, scattered by gas, eventually contributing to the thermal background of the universe. Some hits planets, warming them, driving weather and climate. Some might be absorbed by solar panels, converted into electricity by alien civilizations, if they exist. Energy flowing from stars to planets to space, a continuous cycle powered by nuclear fusion. Eventually, the fuel will run out. Stars will die faster than new ones are born. The galaxy will dim, slowly fading from bright spiral to faint elliptical to dark relic. The era of starlight will end, and Andromeda will enter a new phase, the degenerate era, when the only light comes from cooling white dwarfs and the occasional collision of dead stellar remnants. That era will last far longer than the current one, trillions of years instead of billions. And then even that will end, and the galaxy will go truly dark, just a collection of black holes and scattered atomic nuclei, drifting through empty space. But that's incomprehensibly far in the future. For now, Andromeda shines. For now, stars are being born, planets are forming, maybe life is evolving. For now, the galaxy is vibrant and active, full of energy and motion and change. There's beauty in transience, in knowing that everything is temporary. Galaxies won't last forever. Stars will die. Planets will be destroyed. Even black holes will eventually evaporate. Nothing is permanent except change itself. The universe is a process, not a thing. It's constantly evolving, constantly transforming, never static, never finished. And we're part of that process. We're temporary too, fleeting arrangements of matter, conscious for just a brief moment before dissolving back into the cosmos. Our lives are short, our civilizations shorter still. Everything we build will eventually crumble. Everything we create will eventually be forgotten. From a cosmic perspective, we're ephemeral, insignificant, here and gone in the blink of an eye. But that doesn't make us meaningless. Meaning isn't about permanence. Meaning is about experience, about consciousness, about the subjective quality of existence. We're here now. We can think, feel, love, create, understand. That's meaningful regardless of how long it lasts. A beautiful sunset doesn't need to last forever to be beautiful. A moment of joy doesn't need to be eternal to be valuable. Existence is valuable in itself, not because it endures, but because it happens at all. Andromeda teaches us this. The galaxy has existed for billions of years, but even it is temporary. It will merge with the Milky Way, lose its identity, become part of something else. Does that diminish its current existence? No. It is what it is right now, and that's enough. The future doesn't diminish the present. Change doesn't negate value. Everything is temporary, and that's okay. That's just how the universe works. Let me tell you about one more discovery from Andromeda that changed our understanding of the universe. In 2012, astronomers discovered that Andromeda is surrounded by a massive halo of hot gas, extending over 1 million light-years from the galactic center. This halo contains as much mass as all the stars in the galaxy combined, but it's so diffuse, so spread out, that it's nearly invisible. It only shows up in ultraviolet observations, detected through the absorption of light from background quasars. This discovery revealed something important. The missing baryonic matter, the normal matter that should exist based on cosmological models but couldn't be found, was hiding in these halos, not as stars or gas clouds, but as hot, diffuse plasma surrounding galaxies. It was there all along, we just couldn't see it. This matters because it helps us understand the matter budget of the universe. We know how much normal matter should exist, based on measurements of the cosmic microwave background and observations of primordial element abundances. But when we counted up all the stars and gas we could see, we came up short. About half the normal matter was missing. These galactic halos are where much of it is hiding. And the Milky Way has one too. We're immersed in it, swimming through hot plasma without even knowing it. It extends far beyond the visible disk of the galaxy, perhaps even overlapping with Andromeda's halo. The two galaxies are already touching. In a sense, their halos mingling in the space between them. The merger has already begun, at least in the outermost regions. This gives us yet another way to study the merger. By observing how these halos interact, we can learn about the physics of gas at low densities, the behavior of matter in the intergalactic medium, the processes that will shape Milkomeda billions of years from now. Every new observation of Andromeda reveals something unexpected. Every advance in technology gives us new insights. The galaxy that seemed so simple a century ago, just a faint smudge in the sky, has become a rich tapestry of phenomena, a complex system with structure on every scale from individual stars to the galaxy as a whole. And we're still learning, still discovering, still being surprised. That's the joy of science, the thrill of exploration. Every answer raises new questions. Every mystery solved reveals deeper mysteries. The journey never ends, because there's always more to discover, more to understand, more to wonder about. Consider the individual stars in Andromeda's central regions. They're orbiting the supermassive black hole at speeds approaching a significant fraction of the speed of light. At those velocities, relativistic effects become important. Time dilation means clocks on those stars would run slower than clocks here on Earth. If you could somehow observe a planet orbiting one of those stars, you'd see their days pass more slowly than ours. From their perspective, time is flowing normally. But from our perspective, they're experiencing time dilation, living their lives in slow motion. This isn't science fiction. It's a consequence of general relativity, confirmed by countless experiments and observations. Gravity warps spacetime, affecting the flow of time. The stronger the gravity, the greater the time dilation. Near the event horizon of a black hole, time dilation becomes extreme. A clock falling toward the horizon would appear to an outside observer to slow down, eventually freezing at the horizon itself, taking infinite time to cross. Of course, from the perspective of the infalling clock, nothing special happens. It crosses the horizon in finite time and continues falling toward the singularity. Time is relative, dependent on the observer. These effects are real and measurable. GPS satellites have to account for relativistic time dilation to maintain accuracy. Atomic clocks at different altitudes tick at different rates. Gravity affects time, and the stars orbiting Andromeda's black hole experience this firsthand. Now imagine the most extreme environment in Andromeda. A planet orbiting a star that's orbiting close to the supermassive black hole. The planet would experience tidal forces from the black hole's gravity, stretching it slightly. The night sky would be dominated by the black hole, a perfectly circular void where stars disappear, surrounded by a ring of light from gravitationally lensed starlight. The orbital period around the black hole would be measured in hours or days, not years. And time would flow differently than it does on Earth. Seconds here corresponding to slightly longer intervals there. Could life exist in such an environment? Probably not. The radiation levels would be intense. The tidal forces disruptive. The orbital mechanics unstable. But it's not impossible. Life is resilient. It adapts. Maybe some form of extremophile could survive, thriving in conditions we'd consider utterly hostile. We don't know the limits of life, don't know the full range of environments where it could exist. Every time we think we've found those limits, life surprises us, existing in places we thought impossible. The deep sea vents on Earth, where water temperatures exceed boiling point, host thriving ecosystems. The dry valleys of Antarctica, where it hasn't rained in millions of years, contain dormant microbes waiting for water. Tardigrades can survive the vacuum of space, extreme radiation, temperatures near absolute zero. Life finds a way. Maybe it finds a way in Andromeda too, in environments we'd never expect. Let's return to the cosmic web one more time. Andromeda and the Milky Way are part of a filament, a thread in the cosmic tapestry. This filament connects the local group to larger structures, channeling gas and galaxies along its length. It's like a highway through space, a preferred route for matter to flow. And along this highway, galaxies are moving, pulled by gravity, heading toward regions of higher density. The structure of the cosmic web was imprinted in the early universe, shaped by dark matter. Dark matter formed the scaffolding, the gravitational framework, and normal matter fell into it, accumulating in the densest regions, forming galaxies. The web is mostly dark matter, with galaxies lighting up the nodes and filaments like cities along a highway. Understanding this structure is crucial to understanding cosmology. The distribution of galaxies, the sizes of voids, the shapes of filaments, all of it depends on the properties of dark matter, the expansion history of the universe, the amount of dark energy. By mapping the cosmic web, by measuring how galaxies are distributed, we constrain cosmological parameters, test theories, refine our models. Andromeda is one data point in this vast cosmic survey. Its position, motion, and properties tell us about the structure in our region of the universe, about the local density field, about the gravitational forces shaping galactic evolution. It is part of a larger picture, and understanding it helps us understand the whole. This is how science works. We study individual objects in detail, then connect them to larger patterns, building up a comprehensive understanding piece by piece. Each galaxy is a thread in the cosmic tapestry. Each measurement is a stitch, and slowly, patiently, we're weaving together a complete picture of the universe. There's something profound about this process. We're taking scattered observations, disconnected facts, isolated measurements, and synthesizing them into a coherent whole. We're finding patterns, identifying relationships, uncovering the underlying order. The universe seems chaotic, but it's not. It follows rules, obeys laws, operates according to principles we can discover and understand. That's remarkable. It means the universe is comprehensible, at least in principle. We can figure it out, and Andromeda is part of that figuring out. Every observation of the galaxy contributes to our understanding, adds another piece to the puzzle. We're not done yet. There are still mysteries, still unanswered questions. But we're making progress, steadily advancing, pushing back the boundaries of ignorance. The final chapters of Andromeda's story haven't been written yet. The merger is still billions of years away. Stars are still forming, still dying, still shining. The galaxy is still evolving, still changing, still surprising us. And we're watching, studying, learning. What will we discover next? What new phenomena will we observe? What unexpected features will reveal themselves? We don't know. That's the excitement of science. The future is unknown, full of possibilities, waiting to be explored. But one thing is certain. Andromeda will continue to fascinate us, continue to teach us, continue to inspire us. It's our nearest large galactic neighbor, our future home, our cosmic destiny. And as long as humans exist, as long as we look up at the night sky and wonder, Andromeda will be there, shining in the darkness, waiting to be understood. This journey to the center of Andromeda has taken us across millions of light years, through clouds of gas and dust, past billions of stars, into the heart of the galaxy where a supermassive black hole waits in silence. We've explored its structure, its history, its future. We've contemplated its mysteries, pondered its meaning, marveled at its scale. But the real journey isn't measured in light years. It's measured in understanding, in knowledge gained, in questions answered and new questions raised. It's a journey of the mind, of curiosity and wonder, of the human drive to explore and comprehend. Andromeda represents the frontier of our knowledge, the edge of what we can observe and understand. It's close enough to study in detail, far enough to challenge us. It's similar enough to the Milky Way to provide comparisons, different enough to teach us new things. It's the perfect subject for cosmic exploration, a galaxy that rewards careful study with profound insights. And so our journey ends where it began, looking up at that faint smudge of light in the autumn sky. But now we see it differently. Now we know what it is, what it contains, what it means. We know it's a trillion stars, spinning through space, heading toward us at 250,000 miles per hour. We know it will collide with our galaxy in 4 billion years, creating Milkomeda, transforming both galaxies forever. We know it contains planets, possibly life, maybe even civilizations looking back at us. We know all this because we looked, because we wondered, because we asked questions and sought answers. Because we're human, and that's what humans do. We explore, we discover, we understand. That's our gift, our purpose, our contribution to the universe. We're the cosmos made conscious, the universe awakening to itself, matter contemplating its own existence. And Andromeda is part of that awakening. Every time we look at it, study it, learn from it, we're expanding the sphere of cosmic awareness. We're bringing more of the universe into the light of understanding. We're doing what consciousness does, what it's meant to do. We're witnessing, comprehending, appreciating the grandeur of existence. So look up tonight. Find Andromeda, that trillion-star galaxy, that cosmic neighbor, that future home. See it with your own eyes, those photons that left the galaxy before humans existed, now completing their journey, landing on your retina, triggering a cascade of neural activity that results in perception, in awareness, in understanding. You're seeing across 2.5 million light years. You're looking back in time 2.5 million years. You're witnessing a galaxy as it was when our ancestors were just learning to walk upright, just beginning the long journey that would lead to us, to this moment, to you standing under the stars, looking up, wondering. This is what it means to be human. This is what consciousness makes possible. This is the journey to the center of Andromeda, and it's a journey we're all taking together. Every time we look up and wonder what's out there, the answer is everything. Everything we can imagine and more. 1 trillion stars, billions of planets, uncountable wonders waiting to be discovered. And we're just beginning to explore it, just starting to understand it, just scratching the surface of what's possible. The journey continues. The exploration never ends. And Andromeda will be there, lighting our way, showing us what's possible when we dare to look beyond our own world, beyond our own galaxy, beyond our own limitations. It's waiting for us, patient and eternal, a beacon in the cosmic darkness, calling us forward into the unknown. And we'll answer that call, because that's what explorers do. That's what humans do. We reach for the stars, even when they're impossibly far away. We ask questions, even when answers seem unreachable. We wonder, even when mysteries seem impenetrable. Andromeda is more than a galaxy. It's a symbol of everything we aspire to be. Curious, courageous, persistent, never satisfied with what we know, always reaching for what we don't. Always pushing forward, always exploring, always seeking truth in a universe full of mysteries. That's the real message of this journey. Not just facts about a distant galaxy, but inspiration to keep looking, keep wondering, keep exploring. Because the universe is vast and we are small, but our minds are capable of reaching across that vastness, understanding what we see, finding meaning in the cosmic dance. Andromeda awaits, 2.5 million light-years away, but closer than you think. As close as a glance at the night sky, as close as the curiosity in your heart, as close as the wonder that makes us human. Look up, see it, understand it, and in understanding, find your place in the cosmos. Because we're all part of this story, all connected to that distant galaxy, all participants in the greatest adventure possible, the exploration of existence itself. The journey to the center of Andromeda is everyone's journey. It's the journey of consciousness reaching out to comprehend the universe. And it's a journey that will never truly end, because there's always more to discover, always deeper mysteries to explore, always new horizons to reach. So tonight, when you look up and see that faint smudge of light, remember, you're not just looking at a galaxy. You're looking at possibility, at wonder, at the infinite potential of existence. You're looking at where we came from and where we're going. You're looking at home. Look up on a dark autumn night. That faint smudge of light near the constellation Cassiopeia? That's not a star. That's an entire galaxy, 2.5 million light-years away, containing 1 trillion stars, and it's heading straight toward us at 250,000 miles per hour. Welcome to Andromeda. We're about to take a journey that no human has ever made. A voyage across the cosmic ocean to the heart of our nearest galactic neighbor. And what we'll find there will fundamentally change how you think about our place in the universe. Right now, photons that left Andromeda when our ancestors were learning to make stone tools are just reaching your eyes. Think about that. The light you see tonight started its journey before humans existed as we know them. Before we built cities, before we discovered fire, before we even walked fully upright. That light has been traveling through the void, crossing incomprehensible distances, just to end up in your retina tonight. But here's what really matters. In about 4 billion years, that distance will be zero. Andromeda and the Milky Way are on a collision course. And yes, I said collision. 2 galaxies, each containing hundreds of billions of stars, are going to merge into one. The night sky our distant descendants see will be utterly unrecognizable. If they're still around to see it, let me paint you a picture. Imagine you're standing on Earth 4 billion years from now. You look up, and instead of that faint smudge, the entire sky is filled with Andromeda. Brilliant star clusters, glowing nebulae, the spiral arms stretching from horizon to horizon. It would be simultaneously the most beautiful and terrifying sight imaginable, because at that moment you'd be inside the collision. But let's not wait 4 billion years. Let's go there now. Let's accelerate to impossible speeds and make the journey in minutes instead of millennia. Let's see what Andromeda really is. As we leave Earth behind, our solar system becomes a speck. Then the sun itself vanishes into the star field. We're racing through the Milky Way now, passing stars that have their own planets, their own stories. Some of those stars will die before we reach our destination. That's how far we're going. The Milky Way begins to shrink behind us. We can see its structure now, the spiral arms rotating slowly, the central bulge glowing with ancient stars. And ahead, Andromeda grows larger. First, it's just a smudge, like it appears from Earth. Then it resolves into a disk. Then we start to see structure, spiral arms, star clusters, the dark lanes of dust that wind through the galaxy like cosmic highways. Andromeda is bigger than our galaxy, about twice as many stars. More mass, more gas, more dark matter. It's been devouring smaller galaxies for billions of years, and the evidence is still there. Streams of stars wrap around it like ribbons, the remnants of galaxies that got too close. Andromeda is a cosmic predator, and in 4 billion years, we're next on the menu. As we approach, the scale becomes overwhelming. We're still millions of light years away, and already individual star clusters are resolving in our view. Each one contains hundreds of thousands of stars, bound together by gravity in a dance that's been going on since before Earth existed. Some of these clusters are older than our entire solar system. They've witnessed the birth and death of countless stars, the formation of planets we'll never see, the rise and fall of civilizations that may have lived and died in complete isolation from us. We're crossing into Andromeda's outer halo now. This is a region most people don't even know exists. Ancient stars, moving in vast elliptical orbits around the galaxy's center. These are the elders, the survivors, stars that formed when the universe was young. They contain almost no heavy elements, because heavy elements didn't exist yet. They're made of almost pure hydrogen and helium, the same stuff that came out of the Big Bang. These stars have been wandering through space for over 10 billion years. Earth didn't exist when these stars were born. The sun didn't exist. Our entire solar system is younger than these ancient wanderers. And here's something that should make you pause. Some of these stars likely have planets. But those planets would be barren worlds because they couldn't form the complex chemistry needed for life as we know it. No carbon, no oxygen, no silicon. Just hydrogen, helium, and traces of lithium. Imagine that. Planets that could never host life, orbiting stars that have been burning for twice as long as Earth has existed. We dive deeper into the galaxy now. The star density increases. We're entering the disk where the action happens. This is where new stars are born, where massive nebulae glow with the light of fresh stellar fusion. The disk of Andromeda is about 220,000 light-years across. For reference, our Milky Way is about 100,000 light-years across. We're in the bigger league now. The spiral arms of Andromeda stretch out before us like cosmic expressways. These aren't physical structures, though they look solid enough. They're density waves, regions where stars and gas pile up temporarily before dispersing again. It's like a traffic jam in space, except the traffic jam has been ongoing for billions of years and is made of entire solar systems. We pass through clouds of gas and dust, stellar nurseries where new stars are being born right now. Well, right now by our standards. Really, these stars were born 2.5 million years ago, but the light is just reaching us. Time gets strange at cosmic distances. Every direction you look is also a look backward in time. You're never seeing what is. You're always seeing what was. Inside these nebulae, the temperature is just a few degrees above absolute zero. But hidden within, gravitational collapse is heating pockets of gas to millions of degrees. Stars are igniting, and when they do, their light and stellar winds blow away the surrounding gas, revealing clusters of brilliant blue giants. These stars are massive, maybe 20, 50, 100 times the mass of our sun. They burn hot and fast. They'll die in just a few million years, going supernova and seeding the galaxy with heavy elements. The calcium in your bones, the iron in your blood, the oxygen you're breathing right now, all of it was forged in stars like these. You are quite literally made of stars, not as a poetic metaphor, as a simple statement of fact. We're approaching the center now, the galactic core. This is where things get truly strange. The star density increases dramatically. In our neighborhood of the Milky Way, the nearest star to the sun is over 4 light-years away. Here, in the core of Andromeda, stars can be separated by just light weeks or light days. If you lived on a planet here, your night sky would be ablaze with stars so bright they'd cast shadows. There would be no darkness, ever. Just endless twilight. But there's something else here. something dark. We can't see it directly, but we can see its effects. Stars whip around a central point at incredible speeds. Some are moving at over 1,000,000 miles per hour. The only thing that could make stars move that fast is an enormous gravitational well, a supermassive black hole. This is the heart of Andromeda, a black hole containing the mass of about 100 million suns, compressed into a region smaller than our solar system. It's been here since the galaxy was young, growing slowly over billions of years, feeding on gas and stars that venture too close. And right now, it's relatively quiet, but it hasn't always been. Billions of years ago, this black hole was actively feeding, pulling in vast amounts of matter. The friction and heat from that infalling material would have made the core of Andromeda shine brighter than the entire rest of the galaxy combined. It would have been what we call a quasar, visible across the entire universe. But that era ended. The black hole ran out of easily accessible food. Now it's dormant, waiting, but not dead, never dead, just patient. Around this black hole, in the innermost region, stars are packed so densely that collisions become possible. Not likely even here, but possible. When two stars collide, they can merge, forming what we call blue stragglers. These are stars that look younger than they should be because they've been rejuvenated by collision. Or sometimes the collision is more violent. If a massive star collides with another, the result can be an instant supernova, a stellar explosion without the usual buildup. It's a violent, chaotic environment. And yet, even here, planets might exist. Close orbiting worlds, bathed in the light of dozens of nearby stars, gravitationally bound to stars that are themselves in complex orbits around the galactic center. What would life be like on such a world? Could it even exist? The radiation levels would be intense. Stellar encounters would be frequent. The gravitational environment would be constantly shifting. And yet, life is resilient. If it can exist in the crushing depths of our oceans, in boiling hot springs, in frozen Antarctic ice, maybe it could exist even here, in the most unlikely place in the galaxy. This is what makes the center of Andromeda so fascinating. It's not just a physical place. It's a laboratory for extreme physics. Conditions here don't exist anywhere else in the local universe. And studying them teaches us about the fundamental nature of gravity, matter, and space-time itself. Let's talk about that black hole again, because this is where things get really interesting. Black holes aren't just cosmic vacuum cleaners. They're not just objects with strong gravity. They're regions where space-time itself is so severely warped that the normal rules break down completely. At the event horizon, the boundary of no return, time itself stops from the perspective of an outside observer. Light can't escape. Information can't escape. According to classical physics, nothing can escape. And yet, Stephen Hawking showed us that black holes do radiate. They emit particles through a quantum mechanical process, slowly evaporating over unimaginable timescales. A black hole the mass of Andromeda's central monster would take longer than the current age of the universe to evaporate. But it would evaporate eventually. Everything does. Here's what really bends your mind. If you could somehow survive crossing the event horizon, you wouldn't notice anything special at first. There's no wall, no barrier. You'd just keep falling. But inside, space and time switch roles. What was the future becomes unavoidable in the same way that forward in time is unavoidable in normal space. You can no more avoid hitting the singularity than you can avoid tomorrow. It's not a question of physics anymore. It's geometry. The structure of space-time itself forces you inward. And at the singularity, we don't know. Our physics breaks down. General relativity predicts infinite density, infinite curvature. But infinity isn't an answer. It's a sign that we're missing something. Quantum gravity, the theory we haven't fully developed yet, might give us the answer. But until then, the center of a black hole remains one of the deepest mysteries in physics. But we're not here to fall into the black hole. We're here to witness the core of Andromeda in all its glory. So let's pull back, let's orbit at a safe distance and take in the view. From here, the galactic center looks like a dense sphere of golden light. Old stars, yellow and red, packed together in the central bulge. This bulge formed early in the galaxy's history, when gas collapsed rapidly toward the center, triggering an enormous burst of star formation. Those stars are ancient now, slowly dying, but still shining with the steady light of old age. They'll outlive the blue giants in the spiral arms by trillions of years. Around the bulge, the disk stretches out, spiral arms clearly visible now from our vantage point. We can see the dark dust lanes, the bright emission nebulae, the blue light of young star clusters. It's beautiful in a way that's almost hard to process. This isn't an artist's rendering. This is real. Somewhere out there in that vast collection of stars, there could be planets. And on those planets, there could be life. Maybe they're looking back at us right now at the Milky Way, seeing it as we see them. A faint smudge of light in their night sky. Maybe they're wondering if they're alone. Maybe they've built telescopes. Maybe they're watching us. And here's the thing that really gets me. The light we're seeing right now, if we were actually there, would show us Andromeda as it was 2.5 million years ago. But if there are observers in Andromeda looking at us, they're seeing the Milky Way as it was 2.5 million years ago. We can never see each other as we are now. We're always looking at each other's past. The present is locked away, hidden by the speed limit of the universe. Light can only go so fast, and space is big, unimaginably big. So big that even moving at the fastest speed possible, it takes millions of years to cross the gap between galaxies. This is one of the fundamental truths of the universe. Distance and time are inseparable. Every telescope is a time machine. When we look at Andromeda, we're doing astronomy and archaeology at the same time. Now, let's talk about what makes Andromeda different from the Milky Way. It's not just size. Andromeda's structure tells a different story. Our galaxy has a relatively calm history. Oh, we've merged with smaller galaxies, sure. The Sagittarius dwarf galaxy is being torn apart by the Milky Way's gravity right now, streaming stars across the sky. But Andromeda has been far more violent. Studies of its stellar populations suggest it underwent a massive merger about 2 billion years ago. Another large galaxy, maybe a third the mass of Andromeda, collided with it. The two galaxies merged, and the collision triggered enormous bursts of star formation. The evidence is still visible in the distribution of stars and in the warped structure of the outer disk. Think about what that means. 2 billion years ago, when Earth was inhabited only by single-celled organisms, two galaxies were colliding right where we're looking now. Stars passing within light years of each other. Gas clouds slamming together, compressing, igniting into new stars. The night sky of any planets in either galaxy would have been transformed. Where once there was one galaxy, now there were two overlapping, gradually merging into one. The process took hundreds of millions of years. But at the end, Andromeda emerged larger, more massive, and ready to continue its cosmic expansion. And soon, cosmically speaking, it will be our turn. In about 4 billion years, Andromeda and the Milky Way will begin their merger. The first pass will be dramatic. The two disks will collide, but remember, galaxies are mostly empty space. Stars won't hit each other. The distances are too vast, but the gravitational interactions will be intense. Stars will be flung into new orbits. Some will be ejected from the merging system entirely, cast into intergalactic space to wander forever. Gas clouds will collide, triggering the largest burst of star formation either galaxy has seen in billions of years. The night sky will be transformed. New stars will light up like cosmic fireworks. Then the two galaxies will separate, pulled apart by their own momentum. But gravity is patient. They'll slow, stop, and fall back together. Another pass, another collision. This will happen several times over the course of about 1 billion years. Each time, the two galaxies will lose energy, settling closer together. Eventually, they'll merge completely, forming a single giant elliptical galaxy. No more spiral arms, no more disk, just a vast sphere of stars, slowly aging, slowly dimming, as star formation ceases and the universe continues its expansion. Scientists have already given this future galaxy a name, Milkomeda, or sometimes Milkdromeda, the merger of the Milky Way and Andromeda. And here's the remarkable thing. If humanity still exists when this happens, if we've somehow survived for 4 billion years, we'll witness the most spectacular astronomical event possible. A front-row seat to galactic collision, the ultimate cosmic show. But what about Earth? Will our planet survive? The answer is complicated. The sun will be much brighter in 4 billion years, nearing the end of its main sequence life. Earth might already be uninhabitable, the oceans boiled away by increased solar radiation. But even if Earth is still in the habitable zone, the merger itself poses risks. When the galaxies collide, the solar system could be flung into a completely different part of the merged galaxy. We might end up in the galactic halo, far from the disk, with a night sky full of distant stars but no nearby neighbors. Or we might be thrown toward the center, into a region of high star density and intense radiation. Or, in a worst-case scenario, we might be ejected from the galaxy entirely, sent wandering through intergalactic space. But the chances of Earth being directly hit by anything are essentially zero. Space is too big and stars are too small. Even during a galactic collision, the probability of one star hitting another is astronomically low. It's like throwing two handfuls of sand at each other and expecting individual grains to collide. It just doesn't happen. What does happen is gravitational chaos. Orbits change. Systems are disrupted. But direct collisions, extremely rare. Still, the merger will fundamentally reshape our cosmic neighborhood. The solar system's orbit around the galactic center will change. The constellations we see will be completely different. Stars that were light years away might become our neighbors. Stars that were nearby might be flung to the other side of the galaxy. It will be a cosmic reshuffling on an unimaginable scale. And here's something to consider. Right now, the Milky Way and Andromeda are the two dominant galaxies in what we call the local group. This is a collection of about 80 galaxies bound together by gravity. Most are dwarf galaxies, much smaller than the Milky Way or Andromeda. But when the merger happens, Milkomeda will be the undisputed king of the local group. Its gravitational influence will dominate. And over time, it will continue to grow, pulling in more dwarf galaxies, accreting mass, becoming ever larger. But even Milkomeda won't last forever. The universe is expanding, and that expansion is accelerating. Galaxies that aren't gravitationally bound to us are moving away, and they're moving away faster and faster. Eventually, billions of years from now, the local group will be completely isolated. Every other galaxy cluster, every other supercluster, will be so far away that their light will never reach us. The universe will effectively become unreachable. Future civilizations in Milkomeda, if they exist, will look out and see nothing. Just their own galaxy and a handful of nearby satellite galaxies, surrounded by endless darkness. They'll have no evidence that the universe is any bigger than their local neighborhood. The cosmic horizon will have receded beyond their reach. That's the eventual fate of everything. Isolation, darkness, the heat death of the universe. When all stars have burned out, All black holes have evaporated, and nothing remains but a thin soup of elementary particles, spread across infinite space, at a temperature just above absolute zero. It's bleak, I'll grant you that, but it's also incredibly far in the future. We're talking about timescales that make the current age of the universe look like the blink of an eye. Trillions upon trillions of years. By that point, who knows what will have happened? Maybe life will have found a way to survive. Maybe consciousness will have transcended physical form. Maybe something completely unimaginable will have emerged. The future is long and full of possibility. But let's come back to the present. Back to Andromeda, because there's more to explore here. We've talked about the center, about the black hole, about the merger. But what about the rest of the galaxy? What about the structure, the composition, the mysteries that remain unsolved? One of the most intriguing features of Andromeda is its satellite galaxies. Just as the Milky Way has the large and small Magellanic Clouds, Andromeda has its own collection of smaller companion galaxies. The largest is M32, a compact elliptical galaxy that orbits close to Andromeda's core. M32 is strange. It's very dense for its size, suggesting it might have once been much larger. The prevailing theory is that it had a close encounter with Andromeda in the past, and tidal forces stripped away most of its outer stars, leaving behind just the dense core. It's a galactic remnant, the survivor of a cosmic near-miss. Then there's M110, another elliptical satellite. This one is more extended, less dense, and shows some recent star formation, which is unusual for an elliptical galaxy. Most ellipticals are dead, their star-forming days long past. But M110 still has pockets of young stars, suggesting something has recently triggered star formation. Maybe another close pass by Andromeda. Maybe an interaction with M32. We're still figuring it out. And beyond these larger satellites, there are dozens of smaller dwarf galaxies. Most are so faint they weren't discovered until recently with modern telescopes. They contain only a few million stars, making them incredibly dim. But they're important. These dwarf galaxies are the building blocks of larger galaxies. In the early universe, small galaxies formed first, then merged to create bigger ones. The dwarfs we see today are the survivors, the ones that didn't get swallowed up. Studying them gives us insight into the early stages of galaxy formation, into conditions that existed billions of years ago. There's also evidence of dark matter in these satellite galaxies. A lot of dark matter. In fact, some dwarf galaxies seem to be almost entirely dark matter, with just a few stars visible. These are called ultra-faint dwarf galaxies, and they're among the most dark matter-dominated objects in the universe. They're like ghosts, barely visible, held together by gravity from matter we can't see. And yet, they're there, orbiting Andromeda, bearing witness to the existence of this mysterious substance that makes up most of the universe's mass. Dark matter is one of the biggest unsolved problems in physics. We know it exists because we can see its gravitational effects. Galaxies rotate too fast to be held together by visible matter alone. Galaxy clusters are bound by more gravity than their visible matter can account for. The cosmic microwave background, the afterglow of the Big Bang, shows patterns that can only be explained if dark matter exists. And yet, we don't know what it is. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation at all. It only interacts through gravity. It's invisible, intangible, and yet it's everywhere. Andromeda, like all galaxies, is embedded in a massive halo of dark matter. This halo extends far beyond the visible stars, perhaps 10 times the diameter of the galaxy itself. It's the scaffolding on which the galaxy is built, the gravitational framework that holds everything together. Without dark matter, Andromeda would fly apart. The stars would escape, the gas would disperse, and there would be no galaxy at all. Dark matter is essential to the existence of structure in the universe. And here's a thought that should keep you up at night. If dark matter is everywhere, then it's here too. Right now, as you're reading this, dark matter particles are passing through your body. Billions of them every second. They pass through the earth, through the walls, through you without interacting at all. You can't feel them, can't see them, can't detect them with any sense. They're ghosts in the truest sense, present but intangible. And we're trying to catch them. Experiments deep underground, shielded from cosmic rays, are waiting for the incredibly rare moment when a dark matter particle does interact with normal matter. So far, we haven't had a confirmed detection, but we're getting closer. And when we finally figure out what dark matter is, it will revolutionize physics. Back to Andromeda's structure. The galaxy has a double nucleus. That's right, two bright spots at the center instead of one. For years, astronomers thought this meant Andromeda had two supermassive black holes, perhaps the result of a past merger. But more detailed observations showed the truth is different. There's only one black hole sitting at one of the bright spots. The other bright spot is just a dense cluster of stars, orbiting in a lopsided ring around the black hole. It's an optical illusion, a trick of perspective. But it fooled us for decades. This lopsided ring is actually evidence of past violence. When galaxies merge, the distribution of stars gets disrupted. Instead of a nice, symmetrical pattern, you get lumps and clumps, stars concentrated in certain regions. Andromeda's double nucleus is likely a remnant of its last major merger, still visible 2 billion years later. The galaxy hasn't fully settled down yet. It's still bearing the scars of its violent past. And speaking of violence, let's talk about supernovae. These are the explosions that end the lives of massive stars, and they're some of the most energetic events in the universe. For a few weeks, a single supernova can outshine an entire galaxy. And in Andromeda, with its trillion stars, supernovae are happening all the time. On average, about one every 50 years. That means in the time humans have been observing Andromeda with telescopes, several supernovae have gone off. We've seen some of them. They appear as sudden bright points of light, flare up, then fade away over months. But here's the catch. Because Andromeda is 2.5 million light-years away, the supernovae we see happened 2.5 million years ago. Right now, at this very moment, there could be supernovae going off in Andromeda. But we won't see them for another 2.5 million years. The light is still on its way. And supernovae that we see tonight, their light has been traveling since before humans existed. Since before our species evolved. It's humbling, isn't it? The universe operates on timescales so vast that human history is just a footnote. Supernovae aren't just spectacular. They're essential to life. When a massive star explodes, it creates and disperses heavy elements. Carbon, oxygen, nitrogen, iron, all the elements heavier than helium are forged in the cores of stars and scattered by supernovae. Without these explosions, planets like Earth couldn't exist. There would be no rocky worlds, no water, no organic molecules. Just hydrogen and helium, the primordial elements. So every time you breathe, every time you drink water, every time you look at your hand, remember that the atoms making up your body were created in the heart of a dying star, then scattered across space by a supernova, then gathered together by gravity to form the solar system. You are stardust in the most literal sense possible. Now let's think about planets in Andromeda. We can't see them directly. They're too far away, too small, too dim. Even our most powerful telescopes can't resolve individual planets in another galaxy. But we know they're there. Statistically, they have to be. In the Milky Way, we've discovered thousands of exoplanets, planets orbiting other stars. And we're just getting started. Most stars seem to have planets. It's the rule, not the exception. So if the Milky Way has hundreds of billions of planets, Andromeda, with its trillion stars, must have even more. We're talking about perhaps 1 trillion planets, maybe more. How many of those planets could support life? We don't know. The habitable zone, the region around a star where liquid water can exist, is different for every star. But even conservative estimates suggest there could be billions of potentially habitable planets in Andromeda. Billions. And some of them might actually have life. Maybe simple microbial life. Maybe complex ecosystems. Maybe intelligent civilizations. This is the question that haunts astronomers. Are we alone? Or is the universe teeming with life? The answer has profound implications. If life is common, if it arises whenever conditions are right, then the universe is full of it. Every galaxy, every star system could be home to living organisms. We're just one small part of a cosmic web of life. But if life is rare, if Earth is some kind of fluke, then we might be alone. The only conscious observers in a vast, empty universe. Both possibilities are terrifying in their own way. The truth is, we don't know. We haven't found life anywhere else yet. We've looked, but space is big and our technology is limited. The search continues. Projects like SETI, the search for extraterrestrial intelligence, are scanning the skies for radio signals from alien civilizations. So far, nothing. But absence of evidence isn't evidence of absence. Just because we haven't found anyone doesn't mean they're not there. Maybe they're too far away. Maybe they're not broadcasting. Maybe they existed millions of years ago and are gone now. Maybe they haven't evolved yet. The universe is 13.8 billion years old. Plenty of time for civilizations to rise and fall without us ever knowing. And if there are civilizations in Andromeda, what would they see when they look at us? If they have telescopes like ours, they'd see the Milky Way as it was 2.5 million years ago. They'd see our galaxy before humans existed, before Homo erectus, before our ancestors left Africa. They'd have no idea we're here, and we have no idea they're there. We're separated not just by space, but by time. We're like two ships passing in the night, millions of years out of sync. But maybe someday we'll make contact. Maybe we'll develop faster than light travel, or wormholes, or some technology we can't even imagine yet. Maybe we'll bridge the gap between galaxies. Maybe we'll meet civilizations from Andromeda face to face. Or maybe we'll just exchange messages, radio signals bouncing back and forth across the void, taking millions of years for each reply. A conversation where each response arrives generations after the question was asked. It sounds frustrating, but it would still be meaningful. It would prove we're not alone. And sometimes that's enough. Let's talk about the future of Andromeda. Not the distant future when it merges with the Milky Way, but the nearer future. What will happen to this galaxy over the next few billion years before the collision? Star formation in Andromeda is still ongoing, but it's slowing down. Most of the available gas has already been converted into stars. What remains is spread thin, and much of it is locked up in dying stars or trapped in the gravitational well of the black hole. Over time, star formation will decrease, and eventually it will stop entirely. When that happens, Andromeda will begin to fade. The bright blue stars will die off, leaving only the longer-lived red stars. The galaxy will shift from blue-white to yellow to red, becoming dimmer and dimmer as its stellar population ages. This is the fate of all galaxies in a static universe. They form, they shine brightly for a while, then they fade. But Andromeda won't have a static existence. It's going to merge with the Milky Way, and that merger will trigger one last great burst of star formation. It's like a swan song, a final blaze of glory before settling into quiet old age. And after the merger, after Milkomeda has formed and the fireworks have ended, the new galaxy will slowly dim, becoming a red elliptical, a fossil of past glory. star formation will cease entirely. The remaining stars will burn for trillions of years, but eventually, they too will die. First the massive ones, then the medium ones, then finally the small red dwarfs, the longest-lived stars in the universe. When the last star dies, the galaxy will go dark. Just a collection of dead stellar remnants, white dwarfs and neutron stars and black holes, drifting through space, slowly being pulled toward the central supermassive black hole. And eventually, even the black holes will evaporate. Hawking radiation will slowly bleed them of mass, until they too vanish in a final burst of energy. And then nothing, just empty space, a few particles, and the fading echoes of what once was. That's the ultimate fate of all galaxies. Entropy always wins in the end. But we're getting ahead of ourselves. We're talking about timescales that are almost meaningless. Trillions upon trillions of years. The universe is only 13.8 billion years old. We're nowhere near the end. We're still in the early stages, relatively speaking. Stars are still forming, galaxies are still merging. The universe is still young and vibrant. There's a lot of story left to tell. So let's come back to the present moment. Back to Andromeda as it exists now, 2.5 million light-years away, shining in our night sky. What can we learn from this galaxy? What does it teach us about the universe, about ourselves? First, it teaches us about scale. Andromeda contains 1 trillion stars. Think about that number. 1 trillion. If you counted one star per second, it would take you over 30,000 years to count them all. And each of those stars is a sun, potentially with its own planets, its own solar system. The number of possible worlds in Andromeda is staggering. It makes Earth seem insignificant, and yet, Earth is the only place we know of where life exists. That makes it special, even if it's small. Second, Andromeda teaches us about time. The light we see left that galaxy long before humans existed. We're looking at the past, and in the future, our galaxies will merge. We're part of a cosmic story that spans billions of years, a story that was already unfolding long before we arrived and will continue long after we're gone. We're just a brief chapter in an incomprehensibly long book. Third, Andromeda teaches us about our place in the universe. We're not at the center. We're not special in location. We're in one galaxy among hundreds of billions. Our galaxy is headed toward a collision with another. We're part of a dynamic, changing cosmos, not a static, eternal one. The universe doesn't revolve around us. It doesn't even notice us. And there's something freeing about that. It means we're not burdened with cosmic significance. We can just be. And finally, Andromeda teaches us humility. When you look at that faint smudge in the sky and realize what you're seeing, the sheer magnitude of it, it puts everything in perspective. All our problems, our conflicts, our worries, they're so small compared to the universe. We're living on a tiny rock, orbiting an ordinary star, in an ordinary galaxy, in an ordinary part of the universe. Nothing about our location is special. And yet, we're here. We're conscious. We can look up, see Andromeda, understand what it is, and marvel at it. That's extraordinary. That's what makes us special. Not where we are, but what we can do. We can contemplate the cosmos. We can ask questions. We can seek answers. That's the real miracle. So the next time you're outside on a clear night, find Andromeda. It's not hard. Look for the constellation Cassiopeia, the W-shaped pattern of stars. Andromeda is nearby, a faint oval smudge. You might need to look away slightly, use your peripheral vision. The center of your eye is less sensitive to faint light. But once you see it, once you really see it, you'll never look at the night sky the same way again. Because you're not just looking at a distant object. You're looking at 1 trillion suns. You're looking across 2.5 million years of time. You're looking at our future home, the galaxy will merge with in 4 billion years. You're looking at a place where planets exist, where life might exist, where entire civilizations could be rising and falling while we watch, completely unaware of their existence. And they're unaware of us too. If there's an astronomer on a planet in Andromeda right now pointing their telescope at the Milky Way, they're seeing our galaxy as it was 2.5 million years ago. They're seeing a time before humans, before our species existed. We're invisible to them, separated not just by distance but by time itself. We're like ghosts, haunting different eras of the cosmic timeline. This is the strange reality of living in a universe where light travels at a finite speed. The present moment doesn't exist in any universal sense. There's no cosmic now that stretches across the universe. Every point in space has its own present, its own timeline, all slightly out of sync with each other. Causality connects us, but simultaneity doesn't. It's a consequence of relativity, of the fact that space and time are intertwined. Einstein showed us this over a century ago, and we're still grappling with the implications. But let's think about what we can actually observe about Andromeda right now with our current technology. The Hubble Space Telescope has mapped the galaxy in exquisite detail, resolving individual stars in the outer regions, identifying star clusters, measuring the motion of gas clouds. The Spitzer Space Telescope has looked at Andromeda in infrared, revealing dust that's invisible in optical light, showing us where new stars are forming. The Chandra X-ray Observatory has found X-ray sources, neutron stars, and black holes accreting matter, shining in high-energy radiation. Together, these observations have built up a comprehensive picture of Andromeda, more detailed than any other galaxy except our own. And what we've found is remarkable. Andromeda is a ring galaxy with a strange structure in its central region. Instead of stars distributed smoothly, there's a ring of enhanced star formation about 30,000 light-years from the center. This ring is full of young blue stars, evidence of recent star birth. But why is there a ring? Why aren't stars forming uniformly? The answer lies in resonance. As gas orbits the galactic center, it encounters gravitational perturbations from the spiral arms and the bar-like structure in the inner galaxy. At certain radii, these perturbations reinforce each other, compressing the gas and triggering star formation. It's like pushing a child on a swing. Time it right and small pushes add up to big motion. Time it wrong and nothing happens. The ring is where the timing is right, where gravity's pushes reinforce. But there's more. Andromeda's disk is warped. If you look at the galaxy edge-on, the disk isn't flat. It bends, twisting out of the plane. This warping is common in spiral galaxies, and it's usually caused by gravitational interactions with satellites. In Andromeda's case, the culprits are likely M32 and M110, the two large satellite galaxies. Their gravity tugs on Andromeda's outer regions, pulling the disk out of alignment. Over time, internal forces will flatten the disk again, but as long as the satellites are there, the warping persists. It's a dynamic system, constantly adjusting, never quite settling into equilibrium. We've also detected something called hypervelocity stars in Andromeda. These are stars moving so fast they're escaping the galaxy entirely. They're being flung into intergalactic space at speeds of over 1 million miles per hour. How does this happen? The most likely explanation involves the supermassive black hole. When a binary star system ventures too close to the black hole, the intense tidal forces can rip the system apart. One star falls into the black hole, while the other is flung away at incredible speed, like a cosmic slingshot. These hypervelocity stars are intergalactic exiles, doomed to wander the void between galaxies forever, never to return home. Imagine being on a planet orbiting one of these stars. Your sun was born in a galaxy, surrounded by neighbors, part of a vast stellar community. And then, in a single violent encounter, everything changed. Your star was thrown out, cast into darkness. The galaxy you came from recedes behind you, getting dimmer and dimmer until it's just one more faint smudge among many. Ahead, there's nothing, just empty space, stretching for millions of light years. The nearest star is so far away it's effectively unreachable. You're alone, more alone than anything has ever been. Your descendants, if they survive, will grow up in eternal isolation, the only light in their sky coming from distant galaxies, forever out of reach. It's cosmic exile in the most absolute sense. And yet, hypervelocity stars aren't necessarily dead ends. Some theories suggest they could carry life with them. If a star has planets, and those planets have life, that life could survive the ejection event. The star keeps shining, the planets keep orbiting. From the perspective of someone on the surface, nothing has changed except the night sky. And maybe, just maybe, life could evolve in that isolated system, never knowing it's been cast out from its home galaxy. It would be the ultimate lonely civilization, developing in complete isolation, with no neighbors, no one to contact, no one to learn from. Just themselves, their star, and the vast empty cosmos. Speaking of isolation, let's talk about the space between galaxies. Intergalactic space. Most people think of space as empty, but the space between stars is actually full of gas, dust, and stray atoms. The space between galaxies, though, that's a different story. It's the emptiest place in the universe. In intergalactic space, you might find 1 atom per cubic meter. For comparison, the best vacuum chambers on Earth still have millions of atoms per cubic meter. And out here, between the Milky Way and Andromeda, it's even emptier than average, because both galaxies have gravitationally swept up most of the nearby matter. This is the true void, the closest thing to absolute nothingness that exists in nature. And yet, even here, there's structure. There's what we call the intergalactic medium, a diffuse plasma of ionized gas, heated to millions of degrees by shock waves from galaxy formation and by radiation from quasars. It's invisible to optical telescopes, but X-ray observatories can detect it. This medium connects galaxies in a cosmic web, filaments of hot gas stretching across the universe, with galaxy clusters at the nodes where filaments intersect. The Milky Way and Andromeda sit on the same filament, slowly sliding toward each other along this cosmic highway. This web-like structure is predicted by simulations of cosmic evolution. In the early universe, matter was distributed almost uniformly, with only tiny variations in density. But gravity amplifies tiny variations. Denser regions pull in more matter, becoming denser still, while less dense regions lose matter and become voids. Over billions of years, this process creates the cosmic web, a pattern of filaments and voids that pervades the universe. It's the largest structure that exists, visible across billions of light years. And it's all driven by gravity, the weakest of the fundamental forces, but the only one that acts on cosmic scales without limit. Now, let's address something that often confuses people. If Andromeda and the Milky Way are approaching each other, does that mean the universe isn't expanding? Doesn't expansion push everything apart? The answer is that expansion does push things apart, but only on large scales where gravity isn't dominant. The universe is expanding, meaning the fabric of space itself is stretching. Galaxies that aren't gravitationally bound to each other are moving apart, not because they're traveling through space, but because the space between them is growing. But on smaller scales, where gravity is strong, expansion doesn't matter. The Milky Way and Andromeda are gravitationally bound. We're part of the same structure, the local group, and within gravitationally bound systems, local dynamics dominate. Gravity pulls us together faster than expansion pushes us apart. So we're approaching each other, even as the universe expands around us. In fact, the expansion of the universe is accelerating. This was discovered in 1998, and it was so unexpected that the scientists who found it won the Nobel Prize. We call the cause of this acceleration dark energy, and it's even more mysterious than dark matter. Dark energy makes up about 68% of the universe's total mass energy content. It's a property of space itself, a kind of negative pressure that pushes space to expand faster and faster. We don't know what it is. We don't know why it exists. We can just observe its effects and wonder. Because of dark energy, galaxies that aren't gravitationally bound to us are moving away faster and faster. Eventually, they'll be moving away faster than light can travel. And when that happens, their light will never reach us. The observable universe will shrink. Distant galaxies will vanish from view, not because they've been destroyed, but because the space between us and them is expanding so fast that light can't cross it. It's a kind of cosmic censorship. The universe will hide its distant regions from us forever. But that's a problem for the far future. Right now, Andromeda is still visible, still approaching, still heading toward us. And in the meantime, we have the opportunity to study it, to learn from it, to understand what our own galaxy looks like from the outside. Because that's one of the most valuable things about Andromeda. It's similar enough to the Milky Way that we can learn about our own galaxy by studying it. We can see Andromeda's structure from the outside, see how its spiral arms work, how its central bulge is shaped, how its halo extends. We can measure its rotation, map its dark matter distribution, study its stellar populations. And then we can compare all of that to what we know about the Milky Way. It's like looking at a sibling. Similar but not identical. And the differences tell us as much as the similarities. For example, Andromeda's bulge is more prominent than the Milky Way's. It has a higher concentration of old stars in the center. This suggests that Andromeda formed its central region earlier and more rapidly than the Milky Way did. The two galaxies have had different histories, different patterns of star formation and mergers. Andromeda has been more violent, more aggressive in its growth. The Milky Way has had a relatively calm existence, at least in recent cosmic time. These different histories are written in the structure of the galaxies, encoded in the distribution and motion of their stars. We can also study Andromeda's chemical composition. Different stars have different amounts of heavy elements, depending on when and where they formed. Old stars, formed early in the galaxy's history, have fewer heavy elements because fewer supernovae had occurred yet. Young stars, formed recently, have more heavy elements because they're made from gas enriched by previous generations of stars. By measuring the chemical composition of stars throughout Andromeda, we can reconstruct the history of star formation, see when and where different regions of the galaxy were most active. It's galactic archaeology, reading the fossil record written in starlight. And here's something remarkable. Some of the stars in Andromeda contain elements that were created in our own galaxy. How is that possible? Through intergalactic transfer. When supernovae explode, they don't just disperse material within their own galaxy. Some of that material, especially from the most powerful explosions, is ejected at such high speeds that it escapes the galaxy entirely. It crosses intergalactic space, eventually falling into another galaxy, where it's incorporated into new stars. So there are stars in Andromeda that contain atoms forged in the Milky Way, and vice versa. Our galaxies have been exchanging material for billions of years, long before the merger even begins. We're already mixing, already becoming one system. This intergalactic exchange is part of a larger process called galactic feedback. Star formation and supernovae don't just create new stars. They also drive winds and outflows that push gas out of the galaxy. This gas carries energy and heavy elements into intergalactic space, enriching the medium and regulating star formation. Without feedback, galaxies would form stars too efficiently, converting all their gas into stars in a few billion years. But feedback slows things down, ejects gas, gives the galaxy time to breathe. It's a self-regulating mechanism, one of the many feedback loops that make the universe stable enough for structure to persist. Let's talk about globular clusters. These are spherical collections of stars, tightly bound by gravity, orbiting in the halo of the galaxy. The Milky Way has about 150 of them. Andromeda has over 500. Some of Andromeda's globular clusters are among the most massive known, containing millions of stars. These clusters are ancient, formed in the early universe, and they've survived billions of years virtually unchanged. They're time capsules preserving the conditions of the early galaxy. Studying globular clusters tells us about galaxy formation. The number and properties of clusters depend on the galaxy's history. A quiet galaxy that formed slowly will have fewer, smaller clusters. A violent galaxy that underwent major mergers will have more, larger clusters, formed in the intense star formation triggered by the collisions. Andromeda's large number of globular clusters is more evidence of its violent past. Each cluster represents a burst of star formation, probably triggered by a merger or a close encounter with another galaxy. And within these clusters, strange things happen. Stars are packed so densely that interactions are common. Binary stars form and break apart. Stars collide and merge. In the centers of the most massive clusters, the density is so high that stars can form exotic objects like blue stragglers, which we mentioned earlier, and millisecond pulsars, neutron stars spun up to incredible rotation rates by accreting matter from companion stars. Some globular clusters might even contain intermediate mass black holes with masses between stellar mass black holes and supermassive black holes. We're not sure yet. The evidence is tantalizing but not conclusive. If they exist, they'd be formed from the merger of multiple stellar mass black holes, gradually growing over billions of years. They'd be evolutionary stepping stones, links in the chain from stellar to supermassive black holes. Now, I want to talk about something we haven't discussed much yet: the rotation of Andromeda. Galaxies don't just sit still, they spin. Andromeda rotates about once every 200 million years. That might sound slow, but remember the scale. We're talking about a structure 200,000 light-years across. The outer regions are moving at hundreds of kilometers per second. It's a stately, majestic rotation, but it's there. And here's the thing: the rotation speed doesn't drop off as you'd expect. In a solar system, planets farther from the sun move slower, following Kepler's laws. But in galaxies, stars in the outer regions move just as fast as stars in the inner regions. The rotation curve is flat. This was one of the first pieces of evidence for dark matter. The only way to explain flat rotation curves is if there's more mass than we can see, distributed in a large halo around the galaxy. Visible matter alone can't account for it. Dark matter is necessary. Vera Rubin, the astronomer who first measured flat rotation curves in detail, revolutionized our understanding of the universe with this work. She showed that what we see is only a small fraction of what's there. Most of the universe is dark, invisible, detectable only through its gravitational effects. It was a profound discovery, one that still shapes cosmology today. Andromeda's rotation curve is flat, just like the Milky Way's. Both galaxies are embedded in massive dark matter halos. And when the merger happens, these halos will merge too, combining into one enormous dark matter structure. The visible merger, the collision of stars and gas, will be spectacular. But the dark matter merger will be even more massive, even though we won't be able to see it. It will happen silently, invisibly, two invisible oceans of matter flowing together and becoming one. Let's zoom out for a moment. Let's think about Andromeda's place in the larger cosmic structure. We've talked about the local group, the collection of galaxies including the Milky Way, Andromeda, and about 80 smaller galaxies. But the local group is part of something larger, the Virgo supercluster, a vast collection of galaxy groups and clusters spanning over 100 million light-years. At the center of this supercluster is the Virgo cluster, a massive concentration of galaxies with over 1,000 members. The local group is on the outskirts of the supercluster, slowly falling toward the center, pulled by the collective gravity of all those galaxies. But even the Virgo supercluster is part of something larger. Recent mapping has revealed that we're actually part of an even bigger structure called Laniakea, which means immeasurable heaven in Hawaiian. Laniakea is a supercluster of superclusters, containing about 100,000 galaxies. It's 500 million light-years across. And at its center is the Great Attractor, a gravitational anomaly that's pulling everything in the region toward it. We're moving toward the Great Attractor at about 600 kilometers per second, carried along by the flow of structure on the largest scales. This is the cosmic web in action. Galaxies aren't scattered randomly. They're organized into a hierarchy of structures, from groups to clusters to superclusters to the filaments and voids that span the observable universe. It's all connected, all flowing, all evolving. And Andromeda and the Milky Way are just two small parts of this vast cosmic dance. Now, let's talk about something that might seem trivial but actually matters a lot. The name. Why is it called Andromeda? The name comes from Greek mythology. Andromeda was a princess, the daughter of King Cepheus and Queen Cassiopeia. According to the myth, Cassiopeia boasted that her daughter was more beautiful than the Nereids, sea nymphs and daughters of Poseidon. Poseidon took offense and sent a sea monster to ravage the kingdom. To appease the god, Andromeda was chained to a rock as a sacrifice. But she was saved by Perseus, who killed the monster and married her. After her death, Andromeda was placed among the stars as a constellation, immortalized in the night sky. The galaxy is named after the constellation, which is where it appears in our sky. But there's something poetic about the name. Andromeda the princess was chained, bound, waiting for fate. Andromeda the galaxy is bound too, gravitationally chained to the Milky Way, approaching slowly but inevitably, heading toward a merger that neither galaxy can escape. It's a cosmic fate, written in the initial conditions of the universe, playing out over billions of years. The princess and the galaxy share a destiny, both moving toward transformation. Let's consider the observers. Throughout history, humans have looked at Andromeda, though for most of that history, they didn't know what they were seeing. Ancient astronomers noted the little cloud in Andromeda's constellation, but assumed it was a nebula, a cloud of gas within our own galaxy. It wasn't until 1924 that Edwin Hubble, using the 100-inch telescope at Mount Wilson Observatory, resolved individual stars in Andromeda and measured their distances. He proved that Andromeda was far beyond the Milky Way, a separate galaxy entirely. This was revolutionary. It meant the universe was much larger than anyone had imagined. It meant our galaxy was just one among many. It was the first step toward understanding our true place in the cosmos. Hubble's discovery came just 5 years after the end of World War I, in an era when the world was recovering from unimaginable devastation. Millions had died. Empires had collapsed. The old certainties were gone. And into this fractured world came the revelation that the universe was vast beyond comprehension, full of galaxies we'd never even suspected existed. It must have been overwhelming and liberating. If the universe was that big, then maybe our problems weren't as insurmountable as they seemed. Maybe there was room for hope, for growth, for something better. Hubble went on to discover that the universe was expanding, that galaxies were moving apart, that the cosmos had a history, a beginning. These discoveries laid the foundation for modern cosmology. And it all started with Andromeda, with that one observation that proved we weren't alone in the universe. Not in the sense of finding life, but in the sense of finding other galaxies, other vast collections of stars, other cosmic cities like our own. Since then, every advance in telescope technology has revealed more about Andromeda. We've studied it in every wavelength, from radio waves to gamma rays. We've measured its mass, its composition, its motion. We've counted its stars, mapped its structure, analyzed its light. We know more about Andromeda than any other galaxy except our own. And yet, mysteries remain. One of the biggest mysteries is the nature of dark matter. We know it's there. We can measure its effects, but we don't know what it's made of. Is it a new type of particle, something beyond the standard model of particle physics? Is it primordial black holes, formed in the first moments after the Big Bang? Is it something even stranger, something we haven't thought of yet? Observations of Andromeda, particularly its rotation curve and the motion of its satellite galaxies, provide crucial data for testing dark matter theories. Every measurement brings us closer to understanding this invisible component of the universe. Another mystery is the central black hole. We know it's there, we've measured its mass, but we don't understand how it formed. Did it grow gradually over billions of years, accreting gas and swallowing stars? Or did it form quickly, perhaps from the collapse of a massive gas cloud in the early universe? And how does it interact with the rest of the galaxy? Supermassive black holes aren't passive. They can drive powerful outflows that regulate star formation throughout the galaxy. Understanding this feedback mechanism is crucial to understanding galaxy evolution. Andromeda's black hole, currently dormant, might wake up during the merger, triggered by the influx of gas from the collision. If that happens, the center of Milky could become an active galactic nucleus, shining across the cosmos, visible to distant galaxies, a beacon announcing the birth of a new giant. There's also the question of Andromeda's satellite galaxies. We've found dozens, but simulations predict there should be hundreds, maybe thousands. Where are they? Are they too faint to detect? Were they destroyed in past interactions? Or is there a problem with our dark matter models? This is called the missing satellites problem, and it's one of the challenges facing current cosmology. The answer might tell us something fundamental about how galaxies form, or about the nature of dark matter itself. And then there are the streams. We've detected streams of stars wrapping around Andromeda, remnants of smaller galaxies that were torn apart by tidal forces. These streams are like rivers of stars, flowing through the halo, gradually dispersing. By studying their properties, we can reconstruct the orbit and composition of the galaxies they came from, galaxies that no longer exist as distinct objects. It's like cosmic forensics, piecing together the history of the galaxy one stream at a time. Every stream tells a story. This one came from a dwarf galaxy that orbited too close, was stretched by tidal forces, and gradually disintegrated. That one came from a larger galaxy, maybe a tenth the mass of Andromeda, that merged a billion years ago. Each stream is a chapter in Andromeda's history, a record of growth through cannibalism. And more streams will form in the future. The satellite galaxies we see now, orbiting peacefully, will eventually suffer the same fate. They'll spiral inward, be torn apart, and become streams themselves. Their stars dispersed throughout Andromeda's halo, their identity lost, absorbed into the larger whole. It's a brutal process, but it's how galaxies grow. The universe doesn't preserve small structures. Gravity is relentless, always pulling things together, merging, consolidating. Small galaxies become part of larger ones. Larger ones merge to become giants. And eventually, in the far future, even the giants will merge into supergiants, and those into hypergiants, until the expansion of the universe tears everything apart, leaving each surviving structure isolated in its own pocket of space, alone forever. But we're not there yet. We're in the age of structure formation, the age of galaxy mergers, the age when things are still coming together rather than flying apart. And we're witnessing it, studying it, trying to understand the rules that govern cosmic evolution. Let me tell you about one more feature of Andromeda that I find particularly fascinating. The galaxy has what we call tidal tails, though they're subtle and hard to detect. These are streams of material extending out from the main body of the galaxy, pulled out by gravitational interactions with satellites. Over time, these tails will settle back into the galaxy or be pulled off entirely and become free-floating intergalactic structures. They're transient features visible for just a few billion years before disappearing. And they're evidence of ongoing gravitational chaos, proof that even though Andromeda looks peaceful and symmetric, it's actually a dynamic, evolving system, constantly being reshaped by the gravity of its surroundings. Imagine watching Andromeda evolve in time-lapse, billions of years compressed into minutes. You'd see the spiral arms rotating, stars forming and dying, satellite galaxies orbiting and being torn apart, streams of stars flowing through the halo, the whole structure pulsing and breathing like a living thing. It would be mesmerizing, and it would make clear something that's easy to forget when we look at a single snapshot. Galaxies aren't static. They're dynamic, evolving, responding to their environment. They're shaped by their history and they're shaping their future. They're part of the great cosmic story, and so are we. Which brings me to the philosophical dimension of all this. What does Andromeda mean for humanity? What does it tell us about our future, our purpose, our significance? Some people find the scale of the universe depressing. They look at Andromeda, at those trillion stars, and feel small, insignificant. They think, what does it matter what we do here on Earth when there are trillions of worlds out there? When our entire planet is just one tiny speck in one ordinary galaxy among billions. What difference can we possibly make? But I see it differently. Yes, we're small. Yes, the universe is vast. But being small doesn't mean being insignificant. Think about it. We're the part of the universe that can understand itself. We're matter that has become conscious, that can look out at the cosmos and comprehend what we're seeing. We can measure the distance to Andromeda. We can calculate the mass of its black hole. We can predict the merger billions of years in the future. That's extraordinary. That's miraculous in a sense. The atoms in your brain were forged in stars, ejected in supernovae, gathered into planets, assembled into living organisms, and now they're contemplating their own origin. That's not insignificant. That's the most significant thing in the universe. And here's something else to consider. Right now, as far as we know, Earth is the only place where this is happening. The only place where the universe is awake and aware of itself. Maybe there are others, maybe there are billions of other civilizations scattered across the cosmos. But we don't know that. All we know for certain is that we're here, we're conscious, and we have the capacity to understand the universe. That makes us rare at the very least. And if we're rare, then we're precious. We have a responsibility to preserve that capacity, to use it well, to learn as much as we can before our time runs out. Because time is running out in a sense. Not for the universe, which will continue for trillions of years, but for us, for human civilization as it currently exists. We face challenges: climate change, nuclear weapons, pandemics, artificial intelligence. There are many ways our civilization could fall. And if it does, all the knowledge we've accumulated, all the understanding we've gained, could be lost. Maybe another species would eventually evolve and rediscover it. Or maybe not. Maybe Earth's window for developing technological civilization is limited. And if we fail, the opportunity is gone forever. So when I look at Andromeda, I don't feel small. I feel motivated. because that galaxy represents something we can strive for: understanding, knowledge, the expansion of awareness. We've come so far in just a few centuries. We've gone from thinking the Milky Way was the entire universe to mapping millions of galaxies across billions of light years. We've split the atom, decoded DNA, landed on the moon. Imagine what we could do in another century, another millennium, if we survive. We could send probes to other stars. We could detect biosignatures on exoplanets, proving life exists elsewhere. We could unravel the mysteries of dark matter and dark energy. We could develop technologies we can't even imagine yet. Or we could fail. We could destroy ourselves through war or environmental collapse or technological disaster. We could become just another dead civilization, another failed experiment in the universe's long history. The universe wouldn't notice. It would continue indifferent, but it would be a tragedy nonetheless, not for the universe, but for us, for the loss of all that potential. So Andromeda, to me, is a reminder of what's out there, a reminder of how much we don't know, a reminder that we're part of something larger, something ancient and vast and beautiful, and a reminder that our time is limited. We need to make the most of it. Now let's talk about the practicalities of observing Andromeda. If you want to see it yourself, you don't need a telescope. Binoculars help, revealing more structure and making it easier to find. But under dark skies, away from light pollution, you can see it with your naked eyes. It looks like a faint, fuzzy oval, slightly elongated. That's because we're seeing the galaxy at an angle, not face-on. If Andromeda were oriented face-on, it would look more like a spiral with arms extending from the center. But from our perspective, it's tilted, so we see the disk edge-on, compressed into an ellipse. The best time to see Andromeda is autumn in the northern hemisphere, when the constellation is high in the sky in the evening. But it's visible for much of the year. You just need clear skies, dark conditions, and patience. When you first look, you might not see anything, but let your eyes adjust. Look slightly to the side of where you think it should be. Use your peripheral vision, and then there it is, a faint smudge, easy to miss, easy to dismiss as nothing. But once you know what it is, once you understand what you're looking at, it's impossible to see it the same way again. Some people report feeling emotional when they first see Andromeda. A sense of awe or connection or even fear. There's something about looking at an object so far away, so large, so ancient, that triggers a deep response. It breaks through our everyday concerns and reminds us of the bigger picture. We're not just living on Earth, in our city, in our house. We're living in a galaxy, in a universe, as part of a cosmic story that spans billions of years. That perspective can be overwhelming, can also be liberating. Photography has revolutionized how we see Andromeda. Long exposure images reveal details invisible to the naked eye. The spiral arms, the dust lanes, the star clusters, the satellite galaxies. These images are stunning, some of the most beautiful in astronomy, but they're also scientifically valuable. By analyzing the light in these images, astronomers can determine the galaxy's composition, measure its motion, identify different stellar populations. Every pixel contains information. Amateur astronomers have made significant contributions to our understanding of Andromeda. With modern cameras and telescopes, even backyard observers can capture high-quality images. Some have discovered novae, stellar explosions that flare up suddenly and fade over days or weeks. Monitoring Andromeda for these transient events helps us understand stellar evolution and the life cycles of binary star systems. Citizen science projects have enlisted thousands of volunteers to classify galaxies, including Andromeda's satellites, helping professional astronomers process vast amounts of data. This democratization of astronomy is one of the most exciting developments of recent decades. You don't need a PhD or access to a major observatory to contribute to science anymore. You need curiosity, dedication, and basic equipment. The barriers have fallen, and as a result, more people than ever are engaged with the cosmos, looking up, asking questions, seeking answers. That's beautiful. That's how it should be. Let's consider the technology that has enabled our understanding of Andromeda. The history of our knowledge parallels the history of telescopes. Galileo's telescope, in 1610, couldn't resolve Andromeda. It remained a fuzzy blob. Better telescopes in the 18th and 19th centuries revealed more detail, but couldn't determine the distance. It took the 100-inch Hooker telescope at Mount Wilson, the largest telescope in the world at the time, to finally resolve individual stars and measure the distance. And since then, every new generation of telescopes has revealed more. The Hubble Space Telescope, launched in 1990, has been particularly important. Above the atmosphere, free from the blurring effects of air, Hubble can see with unprecedented clarity. Its images of Andromeda are iconic, showing details down to individual stars in the outer regions. Hubble has measured the motions of stars, mapped the distribution of dust and gas, identified star clusters and supernova remnants. Its contributions to our understanding of Andromeda are immense. And now we have the James Webb Space Telescope, launched in 2021, observing in infrared wavelengths. Webb can see through dust that blocks visible light, revealing hidden star formation regions. It can study the atmospheres of exoplanets, though not in Andromeda, which is too far away. But it's revolutionizing our understanding of galaxy evolution, showing us how galaxies formed in the early universe, how they evolved over cosmic time. And all of this knowledge feeds back into our understanding of Andromeda, helping us place it in context, understand its history, predict its future. Future telescopes will do even more. The extremely large telescope, currently under construction in Chile, will have a mirror over 30 meters across. It will be able to resolve individual stars in Andromeda's central regions, measure their spectra, determine their ages and compositions with unprecedented precision. It will be able to study the dynamics of gas clouds, watch star formation in real time, well, as close to real time as 2.5 million year light delay allows. It will transform our understanding of nearby galaxies. And beyond telescopes, there's another technology that might eventually let us visit Andromeda, at least in a sense: interstellar travel. Right now, our fastest spacecraft, the Voyager probes, are traveling at about 38,000 miles per hour. At that speed, it would take over 16 billion years to reach Andromeda. That's longer than the current age of the universe. Clearly, we need to go faster. Theoretical proposals exist for faster-than-light travel. Wormholes, warp drives, manipulation of space-time itself. But they all require exotic physics, negative energy, conditions we can't create with current technology. Maybe we'll never be able to travel faster than light. The laws of physics might truly forbid it. But even if we're limited to slower speeds, there are possibilities. Generation ships, massive spacecraft, essentially mobile habitats, carrying thousands of people on journeys lasting millions of years. The original passengers would die, but their descendants would continue, generation after generation, born and dying in transit, until finally, millions of years later, the ship arrives at Andromeda. It sounds absurd, impossibly long, but from the perspective of the cosmos, a million years is nothing. And if humanity survives long enough, if we develop the technology and the will, maybe it's possible. Or perhaps we won't send humans. Perhaps we'll send artificial intelligence, machines that don't age, don't need life support, can wait patiently for millions of years while crossing the intergalactic void. They could arrive at Andromeda, study it up close, send back data. By the time the data arrived 2.5 million years later, The civilization that sent the probes might be long gone. But the knowledge would remain, a message from the past to whoever is listening. Or maybe we'll find a way to digitize consciousness, upload minds into computers, transcend biology entirely. Digital beings wouldn't be constrained by aging or resource limitations. They could travel in small, efficient spacecraft, powered by starlight or fusion or something we haven't invented yet. The journey would still take millions of years, but time is subjective. For a digital consciousness, millions of years could pass in what feels like an instant, or could be experienced fully, every moment savored. The choice would be theirs. These are speculations, science fiction more than science. But the point is, the journey to Andromeda, while impossibly difficult with current technology, isn't necessarily impossible forever. If humanity lasts long enough, if we continue to advance, maybe one day, millions of years from now, our descendants will make that journey. They'll cross the intergalactic gulf and arrive in Andromeda. They'll orbit its stars, visit its planets, witness its center up close. And they'll look back at the Milky Way, see it as a faint smudge in their sky, and remember that's where they came from. That's their origin, their ancestral home, receding into the distance as the two galaxies merge. Actually, by the time any such journey could happen, the merger might already be underway. In 4 billion years, the galaxies will be colliding. Any civilization making the journey would be traveling between two galaxies that are in the process of becoming one. The destination and the origin would be merging, creating a confusing, chaotic situation. Where does one galaxy end and the other begin? The answer would be nowhere. They'd be mixed together, a single system. The journey to Andromeda would become a journey within Milkomeda, from one part of the merged galaxy to another. But let's set aside the distant future and return to what we can observe now. Let's talk about the satellites of Andromeda in more detail. M32, the compact elliptical, is particularly interesting. It's one of the densest galaxies known, with stars packed incredibly tightly in its core. The density is so high that stellar collisions, while still rare, are more likely here than almost anywhere else. M32 has likely lost most of its original mass to Andromeda, stripped away by tidal forces during close passes. What remains is the dense, resistant core, a galactic fossil. M110, the other major satellite, is larger and more diffuse. It has a peculiar feature, a disk of young blue stars, evidence of recent star formation. This is odd for an elliptical galaxy, which usually lack the gas needed for new stars. The most likely explanation is that M110 has captured gas from Andromeda or from the intergalactic medium during a close pass. This gas settled into a disk, compressed, and triggered a burst of star formation. It's a reminder that galaxies don't evolve in isolation. They interact, exchange material, influence each other. There are also the dwarf spheroidal satellites, dozens of them, most containing only a few million stars. Some are so faint they're barely detectable. These galaxies are dominated by dark matter, with mass-to-light ratios suggesting they contain hundreds of times more dark matter than visible matter. They're among the most dark matter-rich objects known, making them excellent laboratories for studying this mysterious substance. One particularly intriguing discovery is Andromeda 19, one of the faintest and most diffuse satellites. It's spread out over such a large volume that its average density is incredibly low, lower than the intergalactic medium in some estimates. How it holds together at all is a mystery. Dark matter must be binding it, but the amount required suggests our understanding of dark matter or gravity on galactic scales is incomplete. Objects like Andromeda 19 challenge our theories, push us to refine our models, force us to confront the limits of our knowledge. Another aspect of Andromeda worth discussing is its magnetic field. Galaxies aren't just collections of stars and gas. They have magnetic fields generated by the motion of charged particles, amplified by galactic rotation and turbulence. Andromeda's magnetic field has been mapped using radio observations. It's aligned with the spiral arms, strongest in the disk, weaker in the halo. This field influences star formation, channeling gas flows, affecting the motion of cosmic rays. It's an invisible but important component of the galactic ecosystem. Cosmic rays are high-energy particles, mostly protons, traveling at nearly the speed of light. They're produced by supernovae, by pulsars, by black holes. They fill the galaxy, constantly bombarding everything. On Earth, we're protected by our atmosphere and magnetic field. But in space, cosmic rays are a hazard. Any future travelers to Andromeda would need shielding to protect against radiation. The journey would be dangerous not just because of the distance, but because of the hostile environment of interstellar and intergalactic space. Andromeda also contains neutron stars and stellar mass black holes, remnants of massive stars that went supernova. Neutron stars are incredibly dense. A teaspoon of neutron star material would weigh as much as a mountain on Earth. Some neutron stars are pulsars, spinning rapidly and emitting beams of radiation that sweep across space like cosmic lighthouses. We've detected several pulsars in Andromeda, their regular pulses allowing us to measure their rotation rates, magnetic field strengths, and orbital parameters if they're in binary systems. Black holes are even more extreme. Stellar mass black holes, formed from the collapse of massive stars, typically have masses between 3 and 20 times the Sun. They're invisible unless they're accreting matter from a companion star. When they do, the infalling matter heats up and emits X-rays, making the system detectable. Several X-ray binaries have been found in Andromeda, likely containing stellar mass black holes. Studying these systems helps us understand black hole formation and evolution, the physics of accretion, and the fate of massive stars. Let's consider the question of life in Andromeda more carefully. We've talked about the possibility, but let's get specific. What would it take for life to exist there? First, you need a planet in the habitable zone of a stable star. The star needs to be long-lived enough for life to evolve. Massive stars burn out too quickly. Red dwarfs are longer-lived, but they're prone to flares that could sterilize planets. Sun-like stars are ideal, stable, and long-lived. Andromeda has plenty of them. Second, the planet needs water or some other solvent. On Earth, water is the medium in which biochemistry happens. Maybe other solvents could work, ammonia or methane, but water is the best candidate we know of. Third, the planet needs a stable environment. Too much radiation from cosmic rays or nearby supernovae could be problematic. Too much geological activity could prevent life from establishing. Too little could mean no recycling of nutrients, no tectonic activity to regulate climate. There's a balance required. Fourth, chemistry. You need the right elements in the right amounts. Carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur. The building blocks of life as we know it. Early in the universe, these elements were rare. But by now, after billions of years of stellar nucleosynthesis and supernova enrichment, they're abundant. Any star system forming today in Andromeda would have plenty of heavy elements. Given all these requirements, and given that Andromeda has 1 trillion stars, many of them sun-like, orbited by potentially billions of planets, it seems statistically likely that life exists there. Maybe not intelligent life, maybe not technological civilizations, but at least microbial life. Simple organisms, thriving in whatever niches they can find. If intelligent life does exist in Andromeda, they face the same challenges we do. The tyranny of distance, the speed of light limit, the vastness of space. Even within their own galaxy, communication between star systems would take years or centuries. Between galaxies, it's hopeless. If a civilization in Andromeda tried to contact us right now, their signal would arrive in 2.5 million years. and our reply would take another 2.5 million years to reach them. A single back-and-forth exchange would take 5 million years. Civilizations rise and fall faster than that. Entire species evolve and go extinct in less time. So if there are civilizations in Andromeda, we'll probably never meet them. Not in any meaningful sense. We're too far apart, separated by an unbridgeable gulf of space and time. We're like two people shouting across an ocean so wide that sound waves can't cross it. We can see each other dimly, but we can't communicate. We're alone together, conscious beings aware of each other's existence, but unable to connect. Unless, of course, there's something we're missing. Some physical principle we haven't discovered, some loophole in the laws of physics that allows faster-than-light communication or travel. Quantum entanglement is often suggested, but it doesn't actually allow faster-than-light communication. You can't send information that way. The no-communication theorem of quantum mechanics is quite clear on this. But maybe there's something else, something we'll discover in the future. It's unlikely, but not impossible. Physics has surprised us before. Now, let's talk about something I find particularly fascinating about Andromeda. The galaxy is a time machine, not just in the sense that we're seeing it as it was in the past, but in the sense that different parts of the galaxy show us different stages of stellar evolution. In the spiral arms, we see young stars, blue and bright, burning hot and fast. They're in the prime of their lives, fusing hydrogen into helium, stable and energetic. Some are in clusters, born together from the same gas cloud, siblings in a cosmic sense. In the central bulge, we see old stars, red and yellow, slowly dying. They've exhausted their hydrogen fuel and have moved on to later stages of fusion, if they're massive enough, or are simply cooling as white dwarfs if they're not. These stars have been shining for billions of years. They've witnessed the entire history of the galaxy, from its violent youth to its current middle age. In the halo, we see the oldest stars of all, population 2 stars, metal-poor and ancient. They formed when the galaxy was young, before heavy elements were abundant. They're survivors, witnesses to cosmic history. By studying these different populations, we can reconstruct the galaxy's history. We can see how it formed, how it evolved, how it grew through mergers and star formation. Each stellar population is like a page in a history book, recording the conditions that existed when those stars were born. There's also temporal variation in star formation rates. Andromeda hasn't been forming stars at a constant rate. There have been bursts, triggered by mergers or gas infall, and lulls, when gas supplies ran low. The current star formation rate is relatively low, only about 1 solar mass per year. For comparison, the Milky Way forms about 1 to 2 solar masses per year. Andromeda is in a quiet phase, coasting on past glory. But the merger with the Milky Way will change that. The collision will compress gas, trigger star formation, and for a brief period, geologically speaking, Milkomeda will blaze with the light of newly formed stars. Let's return to the central black hole one more time, because there's more to say. Supermassive black holes don't just sit passively at galactic centers. They regulate galaxy evolution. When they're actively feeding, they emit enormous amounts of energy, driving winds and jets that push gas out of the galaxy. This quenches star formation, preventing the galaxy from forming stars too efficiently. It's a negative feedback mechanism, a thermostat that keeps galaxies in balance. Andromeda's black hole is currently quiet, but it hasn't always been. In the past, it was likely an active galactic nucleus, a quasar, shining with the light of 1 trillion suns. The energy output would have been staggering, visible across the entire universe. Any planets in the central regions would have been bathed in intense radiation, likely sterilized of life. But that era ended, the black hole went dormant, and the galaxy settled into its current state. The black hole will wake up again during the merger. The collision will funnel gas toward the center, feeding both supermassive black holes, ours and Andromeda's. They'll flare up, becoming active galactic nuclei, shining brightly. And then, over millions of years, they'll spiral toward each other, gradually losing energy to gravitational wave radiation. When they finally merge, the collision will be cataclysmic, releasing more energy in a fraction of a second than the Sun will emit in its entire lifetime. Gravitational waves from the merger will ripple across space, carrying news of the event to distant galaxies. Future gravitational wave detectors might observe similar mergers in distant galaxies, giving us a preview of what will happen here. The merged black hole will be even more massive, containing the combined mass of both progenitors, over 150 million solar masses. It will settle into the center of Milkomeda, the gravitational anchor around which the new galaxy rotates, and it will wait, patient and eternal, for the next meal, the next galaxy to merge with, the next chapter in its growth. Black holes are patient. They have all the time in the world. Longer, actually. They'll outlive the stars, outlive the galaxies, outlive everything except the universe itself. And even then, they'll eventually evaporate through Hawking radiation, returning their mass energy to the void. But that takes so long, such incomprehensibly long timescales, that it's barely worth considering. For all practical purposes, black holes are eternal. Let's shift gears and talk about something more immediate, more human: the cultural impact of Andromeda. This galaxy has captured human imagination for over a century. It appears in science fiction, in art, in philosophy. It represents the unknown, the unreachable, the vast frontier beyond our own galaxy. Isaac Asimov wrote about Andromeda. Arthur C. Clarke referenced it. Countless science fiction stories have used it as a setting, a destination, a home for alien civilizations. It's become a symbol, representing not just itself, but all galaxies, all the unreachable places in the universe. When people think of other galaxies, they often think of Andromeda because it's the one they can see, the one they can point to in the sky. There's something poignant about that. Andromeda is the closest large galaxy, and yet it's so far away we'll never reach it, at least not with current technology. It's visible but untouchable, knowable but unreachable. It represents the limits of human ambition, the boundaries of what's possible. We can study it, we can understand it, but we can't go there. Not yet, maybe not ever. But that doesn't diminish its importance. Understanding Andromeda is valuable in itself, not because it leads to practical applications, but because it expands our knowledge, satisfies our curiosity, feeds our sense of wonder. Science isn't just about utility. It's about understanding, about answering the fundamental questions. What is the universe? How does it work? Where did we come from? Where are we going? Andromeda helps us answer those questions. It's a laboratory, a test case, a comparison point. By studying it, we learn about galaxy formation, stellar evolution, dark matter, black holes, cosmic structure. We learn about the universe, and in doing so, we learn about ourselves. Because we're part of the universe. We're not separate observers, looking at the cosmos from outside. We're inside it, made of it, shaped by it. The atoms in our bodies were forged in stars like those in Andromeda. The physical laws that govern galaxies also govern us. We're connected fundamentally to everything out there. Understanding Andromeda is, in a sense, understanding ourselves. This is why astronomy matters. It's not just about cataloging objects in the sky. It's about understanding our place in the cosmos, our connection to the larger whole. It's about perspective, about seeing beyond our immediate concerns and recognizing that we're part of something vast and ancient and ongoing. When you look at Andromeda, you're seeing photons that have traveled for 2.5 million years. Those photons left the galaxy before humans existed. They've crossed the intergalactic void, passed through the Milky Way's outer halo, traversed our solar system, entered Earth's atmosphere, and landed on your retina. That's their journey. And your journey, if you think about it, is equally remarkable. You're a collection of atoms that was once scattered across the galaxy, maybe across the universe. You were assembled by chance and physics into a living, conscious being. You can think, feel, wonder. You can look up at the sky and understand what you're seeing. That's astonishing. So Andromeda isn't just a galaxy. It's a mirror, reflecting back to us the grandeur and mystery of existence. It's a question asking us to ponder our place in the cosmos. It's a challenge, daring us to reach beyond our current limits. And it's a promise, suggesting that there's always more to discover, more to learn, more to understand. The journey to the center of Andromeda is a thought experiment, a way of exploring what's out there and what it means. We can't physically make the journey, not yet, but we can make it intellectually, imaginatively, scientifically. We can study the galaxy, map its structure, understand its history, predict its future. We can send our telescopes and instruments as proxies, gathering light and data, bringing back knowledge. And in doing so, we expand the boundaries of human understanding, push back the frontiers of ignorance, illuminate the darkness with the light of knowledge. That's the real journey, not the physical traversal of space, but the intellectual traversal of mystery. Every question answered raises new questions. Every discovery reveals new puzzles. Science is an endless frontier, and Andromeda is one of its most beautiful landscapes. As we conclude this journey, let's take one last look at the galaxy. From our vantage point, orbiting at a safe distance, we can see it in its entirety. The spiral arms, glowing with young stars. The central bulge, dense with old stars. The dark dust lanes, winding through the disk. The satellite galaxies, orbiting like moons around a planet. The streams of stars, remnants of past mergers. The invisible dark matter halo, holding everything together. And at the very center, the supermassive black hole, silent and waiting. This is Andromeda, a trillion stars, bound together by gravity, rotating slowly through space, heading inexorably toward us. In 4 billion years, it will collide with the Milky Way. The merger will be spectacular, transforming both galaxies beyond recognition. New stars will form, old stars will be flung into new orbits, and the two central black holes will eventually merge into one. The result will be Milkomeda, a giant elliptical galaxy, the dominant structure in the local group. But for now, Andromeda exists as it is, a magnificent spiral galaxy, shining in the night sky, waiting for us to look up and see it. It's been there for billions of years, and it will be there for billions more. It's older than Earth, older than the Sun, a relic of the early universe, a survivor of cosmic evolution. And we, tiny beings on a tiny planet, can observe it, study it, understand it. We can measure its distance, calculate its mass, predict its fate. We can see across 2.5 million light years and comprehend what we're seeing. That's the power of human intelligence, the triumph of scientific inquiry. We're small, yes, but we're not insignificant. We're the universe looking at itself, matter contemplating matter, consciousness emerging from chaos. Andromeda reminds us of that. It reminds us that we're part of something larger, something magnificent, something worth preserving and studying and celebrating. It reminds us to look up, to wonder, to ask questions. It reminds us that the universe is vast and full of mystery, and that we have the capacity to explore it, not with our bodies perhaps, but with our minds. So look up tonight, find Andromeda, that faint smudge of light in the autumn sky, and remember what you're seeing. a trillion stars, a sister galaxy, our future home, a cosmic neighbor, heading toward us across the void, patient and inexorable. Remember that those photons hitting your eye left Andromeda before humans existed, before our ancestors even walked upright. Remember that you're looking across space and time, seeing the past, witnessing cosmic history. And remember that you can do this. You, a human being, a product of evolution on a small planet, can look up and understand the universe. You can measure it, comprehend it, predict it. That's remarkable. That's what makes us special. Not where we are, but what we can do. Not our size, but our capacity for understanding. Andromeda is out there, waiting. A trillion stars, spinning slowly through space, heading toward us. And we're here watching, learning, growing. We're embarking on the greatest journey possible. The journey of discovery. The exploration of the cosmos through science and reason. It's a journey without end, because there's always more to learn, more to discover, more to understand. The center of Andromeda holds mysteries we're only beginning to unravel. The supermassive black hole, the dense star clusters, the exotic physics. But we'll get there eventually. Not physically, maybe, but intellectually, certainly. We'll understand it, map it, explain it. That's what we do. That's what makes us human. This is the journey to the center of Andromeda. Not a physical voyage, but an intellectual one. A journey through knowledge, through understanding, through wonder. And it's a journey worth taking, because at the end, we find not just knowledge about a distant galaxy, but insight into ourselves, into our place in the universe, into what it means to be conscious beings in a vast and ancient cosmos. The universe is big. Andromeda is far away, but we can still reach it with our minds, with our telescopes, with our theories and equations. We can still understand it, still learn from it, still be awed by it. And that's enough. That's more than enough. That's everything.